This video is on LeChatlier's principle. His name, he is in fact French. Okay, so what is LeChatlier's principle? It states that if stress is applied to a system in dynamic equilibrium, the system changes in a way that will relieve that stress. Okay, molecules do not like to be stressed out, just like you do not like to be stressed out. Okay, they will adjust so that they are not stressed. Okay, if you are hot, you might turn on the air conditioning. Okay, that is how you relieve stress. What the equations always want to do, what chemicals like to do, is restore their equilibrium. Okay, equilibrium is where they would like to be. Okay, when you change that, that is what stresses them out. So the way that they can actually restore this is by shifting the equation to either the reactants or the product side. So it'll actually move the reaction side by side. And now we can kind of see the purpose of these double-sided arrows, right? These equilibrium arrows. They can go both ways because reactions are going to shift forward in the forward direction and then in the reverse direction. So there's going to be three things that you could do to cause stress to an equation. The first thing is to change the concentration, okay? So you would do this by adding in an amount of some kind of reactant or product. So basically you're just going to add more of something. So if we add some reactant, what that's going to do is going to push it to make more product. Okay, that means it's going to shift towards the product. That's in the forward direction. If we add some products, then it's going to shift towards the reactant side. Okay, that's the reverse direction. So I'm going to show you guys a quick kind of physical example so you can kind of see what I'm talking about and physically see it. All right, so we have here one of the reactants is orange, and then one of the products is yellow. Okay, so what's going to happen when this person adds some acid to it or adds some base to it? What's going to happen? Okay, so this product is currently yellow. Okay, and they are going to add in acid to this equation. And you can see when they add in the acid, it turns orange. Okay, so I just want to pause for a second, kind of take us back to look at this equation so you guys can see what I'm talking about with an equation. Okay, so here's the acid over here on the right, and there's the yellow that we started with. And when you put them together, it's going to shift back towards the left and make the orange. Okay, you're adding the acid in there with the yellow part. Let's watch it again. So here's a product. We're adding acid to it, and what that's doing is going in the reverse direction and making that orange reactant. Okay. Second part of this is then she is going to add in some base, right, some hydroxide. And what that's going to do is shift it in the forward direction. Okay, so this is an equilibrium shift. All right, so second thing that can cause stress is a temperature change. We've obviously seen lots of ways that temperatures affect reactions. It will shift towards the reactants or products depending on whether it wants to absorb or release energy. So this is kind of where those thermochemical equations come in, where the heat is actually part of the equation. I just kind of think about it like another reactant. Okay, we don't have to do any thermochemical math or anything like that. And our third stress is going to be pressure. Okay, so pressure is always going to shift to relieve that pressure. Okay, and we have to remember, kind of think back to gas laws. What is pressure, right? Pressure is when molecules are colliding with the walls. That's what actually causes that pressure. So how can you relieve that stress, right? How can you make them not collide with walls? Basically, if there's less molecules on one of our reactants or product sides, that means there's going to be less pressure there. If there's more molecules, there's going to be more pressure. So we're going to have to look at the type of molecules present on each sides of our reaction. All right, so let's look at some examples. All right, so first example is that we're going to have some nitrogen dioxide, and that's going to be in equilibrium with some dinitrogen tetroxide, and it is an exothermic reaction, and it releases 57.2 kilojoules of heat. Okay, so these questions are always going to give you some kind of equilibrium equation. So it is going to ask us what's going to happen if we increase the nitrogen dioxide. So again, anytime something is being added or removed, we're not going to look at that one. So I'm just going to put a little X here. Whatever you're changing, we can't really look at that because it gets kind of confusing. Okay, this one's actually going to shift to the right side. And I think the best way to kind of explain that is using like a scale. Okay, this is all about balance. This is all about equilibrium. So let's look at a little wonderfully drawn scale here. And I invite you to draw one for yourself too. If you're not sure, this is a really good visual to think about it. Okay, so on one side we have our N2O4, and on the other side we have NO2. Well, we are increasing this NO2, right? So I'm going to add a couple more over here. This scale is now unbalanced, right? It's now leaning down and it's not equal. Okay, so how can we relieve this stress and balance them back out again? Okay, we need to make some of the reactants into products. Okay, it's going to shift over this way. So that's why it's going to shift to the forward direction. It's going to shift to the products because we have too much NO2, so we need to make more of the N2O4, which will also make more heat. Okay, it's going to make more of everything on the right side. All right, second question. I'm going to keep my little scale up here because I think it's a really good visual for us to use. All right, so second question will be what's going to happen if we decrease the amount of NO2, right? What happens if we remove that? Okay, so in this case, we have lost some of this NO2. Again, whatever it's asking about, we're just going to put an X in that spot because it gets a little confusing on whether that should go up or down. Okay, so on our scale, we have lost the NO2, it's gone. Okay, so if there's nothing in that bin, that means this part of the scale would rise up, right? And that right side would kind of sink down because it gets heavy. Okay, so here's our current scale, and that's no good. So how can we balance it out? There are always more than one molecule there, so I'm just kind of drawing some extra ones. So what's going to happen here is that some of our N2O4 is going to shift, and some of that N2O4 is going to become NO2 in order to balance its back out. So this one is going to shift in the reverse direction. It's going to shift to the left. In order to do that, we have to lose some N2O4 and we have to lose some heat in order to create that stuff that's on the left side. Okay, I hope that scale was helpful. I'm going to try to do some examples without it, but keep that nice visual in your mind. Okay, third kind of example, what's going to happen if I increase the temperature? Okay, just think of temperature as another reactant or product. Okay, so I'm just going to put a little X in that spot. So if I'm adding in temperature on the product side, okay, just think about it like another molecule. Okay, I got 3 molecules on top. We added more over here, but we need to get rid of those to keep it balanced. So it's going to shift away from the heat, okay, which means that we are going to make more of the NO2. And if you're making more of the NO2, that means you had to lose some of your N2O4, okay, because some of that had to be used up in order to make the NO2 as well. Okay, so that one's going to go down. So one side note that a lot of students find helpful is kind of looking at the direction of the arrow, okay? If it's pointing towards something, that side's going to go up. And if it's, so like you can see in the first one, it's pointing towards those green arrows, those are going up. Bottom one's pointing to the left, that's going to go up. The tail end of the arrow is going to go down, okay? So every time you have a tail side of the arrow, that's going to be lower. Some students find that helpful once they decide which way the arrow is kind of pointing. So if it's pointing one direction, that side goes up and the other side goes down. Some students find that helpful as well. All right, second example. For this one, I really want you guys to try it out for yourself, okay? I'm going to write the different prompts on the side, and I want you to pause the video, think about it, try it out for yourself, see if this is making sense, see if you're understanding it. If not, you can always shoot me an email, and I can help you figure that out, okay? So try these different prompts. So the first thing is what happens if we increase the temperature of the reaction. Second one is going to be what happens when we add more oxygen. What's going to happen if we then remove the oxygen? And then last question here, this one we have not talked about, so you're going to have to just kind of skip this one in our figured out stage, is what's going to happen if you increase the pressure. Okay, so take a second, pause the video, try it out, and I am going to go through all of these. Okay, so first one, I'm just putting a little X here on the heat. If you're adding heat, that means that we need to move away from that, which means we're going to use up the SO2 and we're going to make more of the SO2 on the right side and the O2 on the right side. So second one, I'm going to little X by this oxygen. We're adding that, which means we need to push away from it. We're going to lose SO2 on the right side and we're going to increase in the SO3 and the heat. Okay, next one, we're removing oxygen. So if we're removing it, that means we need to fill that gap. We're going to need to make more of those, okay? So we're going to add more on the right side, okay? So we're going to push towards that. So that means the SO2 is going to go up, the heat's going to go down, and the SO3 is going to go down. All right, so those are the ones you should be able to do. Now this last one, pressure, okay, I said pressure depends on the molecules. So over here, we have two of, they should be SO3s, and on the other side, we have two SO2s and an oxygen, okay? So we have two molecules on the left and three on the right. The more molecules there are, the more pressure there is, okay? So the right side has more pressure and the left side has less pressure. So if we're increasing the pressure, this right side has more of that, okay? If we're increasing the pressure, we want to move away from that. We do not want pressure. So we're going to shift to the left, and we're going to move away from the pressure. That means that the SO2 and the oxygen are going to go down, and that the heat and the SO3 are going to go up. And that is just because of the molecules that are present.